So questions from the homework. Number 3. I would temporarily let a equal a half x. So I'm going to solve this cos a equals root 3 over 2. We're going to end up being here and here because cosine is positive. I think you're going to find it's the 1, 2, root 3 triangle. And I think cosine, 1, 2, root 3, does the reference angle end up being pi by 6? Okay, so I'm skipping a few steps in the interest of time. So you get the first a value is pi by 6, and the second a value is, correct me if I'm wrong, 11 pi by 6, yes? Is that okay so far, Dominique? Because it's 12 pi by 6 all the way around. Then we would say, going back to this line, how would I get the x by itself? How would I get the x by itself? I think here I would times a by 2. Yes? So I think the first x value is going to be timesing a by 2. It's not going to be 1 pi by 6. It's going to be 2 pi by 6, which is really pi by 3. And the second x value is not going to be 11 pi by 6. It's going to be 22 pi by 6, which is 11 pi by 3, which sadly actually is outside of my domain between 0 and 2. Oh no, they wanted the general solution. I stand corrected. They didn't say between 0 and 2 pi. Number 3 said find the general solution. So, okay, there's my 2 primary angles. And you know what? Since both of these do reduce, I will this time write this as pi by 3 and 11 pi by 3. The other thing I would have made a note of is the period. The period is 2 pi over b, which in this case is 1/2. The period ends up being 4 pi. So if they want the general solution, it's going to be both of these, and I apologize for the strange way of writing this, plus multiples of 4 pi, where n is an integer. Or you could have written that instead of 4 pi, you could have said, just to make the math easier, well, those are thirds, let's make that 12 pi over 3, and I would have taken that too. But since I didn't actually need to calculate any more of them, I got really lazy and didn't even bother finding a common denominator, and okay, yeah, I'll take that too. Is that all right? I hope that's what it says in the back. That's it. Whew. I had 3 days off too, so my math skills could be rusty. It's going to be one of these on the written, and I'm pretty sure it's even going to be the first question on the written section. It's going to be a period change. Oh, and I'll even be more blatant. That number right there, that number in front of the x, it's going to be a 1/2 or a 1/3 or a 2 or a 3 or maybe a 4 at the most. It's not going to be a 7, because a 7 would mean you're finding 14 solutions, which would be way too much work. Or a 6 would mean you're finding 12 solutions, which would be way too much. So I kind of told you what the question is, pretty close. Any others? We're going to spend today and all of our first and probably second weeks back on the single toughest topic in all of Math 12. I really debated, did I want to start or did I want to finish? I also have a take-home quiz for you, but I don't want to give you homework over spring break. So I'm going to give you your first take-home quiz on quadratic trig equations and solving equations using a graphing calculator and solving equations with period change on Monday when we come back. Okay? Then I have another almost identical quiz on Wednesday when we come back. And then we'll start doing some quizzes that involve today's topic, which is the wonderful world of trig identities. Finally, I'm going to give you a formulas sheet for this course. Let me pause. So I've just handed out your formula sheet, and on the gray one, you are allowed to make little notes, little memory aids, write whatever you want to that will help you study on this. And here's the first thing I'm going to say to you. First of all, these are called identities. These are all the trig identities, basically the entire top half or top third of the sheet. The ones you're going to need to memorize, and you will because you're naturally lazy, but the ones you're going to need to memorize, you might want to underline that one, this one, this one. Now, you should also know these three, but I think you already know these three. I think you already know that secant is 1 over cosine. Yes? I tried to drum that in. And that cosecant is 1 over sine. Yes? And that cotangent is 1 over tangent. What's the point of these? We are going to introduce you to the concept of proofs, of proving something. And when you're trying to prove something, you're under certain limitations. There's a certain structure that must be followed. If you would be so kind as to turn in your books to lesson 5, which is page 335. 335. And you want to keep said yellow or said gray sheet out and handy. The formula sheet, keep one near you. First, I got to give you a bit of a definition. In mathematics, it's important to understand the difference between an equation and an identity. This is an equation. The reason it's an equation is it's only true for certain values of x. The only x's that work in here are -2 and +2. Nothing else does. It's not an equation because there's an equal sign. It's an equation because there are only a few limited select values that work. This is an identity because the left side and the right side are actually the same. They can be rewritten to look like each other, and any legitimate or legal values of x are true. You've seen identities already without realizing that you had seen identities. Let me give you a good example of one from way back in the logarithm days. Oh, get that right, Mr. Dueck. Those were equivalent forms of the same expression for all legal values of x and y. What were the legal values of x and y? Oh, you can't take the log of a negative. Oh, and the base couldn't be negative or 1. That's an identity. Now, I called it, we called it a rule, I think. I said to you, what's dividing 2 logs the same as? And all of you would have said, that's like subtracting. That's, oh, here's another log identity that we gave you. What was the power rule for logs? How could I rewrite that? Do you remember? It's good brushing off the cobwebs. We said these were equivalent. Doesn't work that that doesn't mean necessarily that they work for every single x out there. The domain of this is not all reals, but they work for any legitimate value of x, and any allowable value of x, any value of x bigger than 0. Okay. We gave you this one. The base change rule, we called it. It was actually an identity. What we're going to be looking at is we're going to build up about a half dozen trig identities that we have on your yellow formula sheet. And we're going to try and use those to prove far more complicated ones. That's the strategy. What are the very, very basic trig identities? Well, I snuck these in the last unit. We're going to start off with these 3, but we're never going to come back to, well, these 4 if I count x squared plus y squared equals r squared. But we're never going to come back to these after today. We know that sine is y over r, cosine is x over r, tangent is y over x, and x squared plus y squared equals r squared. We also met the reciprocal identities. These ones are on your formula sheet. We can use these to prove the quotient and Pythagorean identities. And we're going to use these 2 to prove a whole bunch of other stuff. Before doing this, we will verify some identities for a particular case. Next page. I think you have to turn the page. We will often give you an identity in what's called a t-table or a t-chart. Why is it called a t-table or a t-chart? Because this looks like a letter T. Here's the problem. There is an equal sign right there, but Vlad, we're trying to prove that they're equal, which means we can't assume that they're equal in order to prove that they're equal. None of our equation solving rules are allowable. We can't add 5 to both sides, even if that would make things way easier. Or we couldn't divide both sides by tangent, even if that would make things way. You can't do the same thing to both sides, because that would be assuming they were equal in order to prove that they're equal. Can't cross multiply, even if that would make things way easier. That'd be assuming they were equal in order to prove that they're equal. Now you can convince yourself that they're equal intuitively by trying to see if a certain case works. So here's what it says. This technique doesn't prove that identity is true for all values of the variable, only for the value of the variable being verified. It says double check, is tangent of x the same as the sine divided by the cosine for 60 degrees? Okay, let's put our calculators back in degrees one more time. Oh, mine already is. And find the tan of 60. You get 1.732. Now go sine 60 divided by cos 60. Sine 60 divided by cos 60. Do you also get 1.732? So I think they're the same. Is that an actual proof? No. All you've given me is one example that works. So you can use this trick, you can use this method, Ryan, just to see if it does work. That might help you on a multiple choice identity, for example. You might say, I'm stuck. Oh, heck, why don't I just try plugging in an angle into the original question and look at my 4 answers. I'll plug in that same angle, and I'll see which of those 4 answers gives me the same decimal. Oh, and I'll double check it for a second angle just in case it fluked out to the same ones. That's not going to get you very far on the written and on most multiple choices. So we could also do it over here. If we plugged in pi by 6, you would find that tan squared plus 1 is actually equal to secant squared. Tangent times tangent plus 1 is equal to secant times secant. It is. What we are much more interested in is proving identities. However, we have to treat the left side, abbreviation LS, and right side, abbreviation RS, separately. We cannot, for example, multiply both sides by cosine, even though that might make it way easier, because that would be assuming it was equal in order to prove that it was equal. It says, remember, don't make the mistake of assuming the answer by writing left side equals right side at the start of a proof. Don't move terms from one side or the other. Here's how I do a proof. Okay. First thing I will do, if they haven't already, is I'll write down the left side on one side of the t and the right side on the other side of the t. By the way, it added a restriction. It said, oh, no, cos theta can't be equal to 0. Why can't cosine of theta work out to 0? Why do they have to be careful and add that restriction? Okay, can't divide by 0. We're going to be sloppy in most of our identities, Ellen. We're going to assume that you know the restrictions. We're going to, in the first couple, mention the restrictions, and then we're going to say, ah, forget it. Now, eventually, since you have this on your formula sheet, we're going to use this to prove other stuff. But we should first prove this. And the only way I know of to prove this one is to go back to x and y and r. Tangent is what over what in terms of x and y and r. Cosine is equal to what over what? Sorry, sine is equal to what over what in terms of x and y and r? Divided by x over r. Oh, on the right-hand side there, I have a fraction divided by a fraction. How do I divide by a fraction? So this is the same as y over r times r. You know what? I shouldn't use an x for a times sign, should I? Because that's going to look like an x. I'll use a dot. Oh! Alex, what do you notice here? And what am I left with? on the top? And what am I left with on the bottom? And what did I have on the left side? I've just proved it. Am I somewhat of a nerd? So I will show you what I was taught with proofs, okay? There is a tradition that goes back about 600 years that when you did a proof, because originally most math was done in Latin, that you would write at the end of a proof QED, which stood for quote ertas demonstrandum, which means which was to be demonstrated. That's what I was trying to show. We used to joke in university that it stood for question easily done and was the biggest lie on earth, because most of my proofs in university took 3 or 4 pages as opposed to 2 lines. I will traditionally write that. You don't have to, but I will. That's sort of my, when they get a touchdown, spiking the touchdown ball. That's my touchdown dance right there. I did it. You will see some teachers, they will do this. Don't write this down. What do you think LHS equals RHS stands for? Left-hand side equals right-hand side. Then you have the Americans, which have to do things their own way and are lazy. They would just draw a little square and color it in. That's boring. I'm a nerd. I always write QED. There's a proof. Now, we're not going to go back to Y and X and R to prove this anymore. We now know that wherever I see a tangent, it's the same as what, Mitsu? Read that. Whenever I see a tangent, I can replace it with a sine over cosine if I'm doing a proof. That's going to be one of our first steps. And it's on your formula sheet, but that's one you'll memorize because you use it so often. In fact, if you don't have that memorized, then I know you haven't done any of the homework in your flunky test. Next page. It says, use the basic identities to prove this. That 1 plus tan squared equals secant squared. Okay. I'm going to draw my t-table. Yoink. Secant squared. Well, what was secant in terms of x and y and r? Careful now. Secant goes with what? Cosine. So if cosine was x over r, secant is? What would secant squared be then? R squared over x squared. Yeah. I'm trying to prove that the left side works out to that. By the way, you'll usually spend far more time on the uglier side, which I think is the left side. It's got more terms. 1 plus, what was tangent? What over what in terms of x and y and r? Y over x. So what would tan squared be? Carly, is this a fraction? Is this a fraction? Is this a fraction? Yes. What is it as a fraction? What over what? I never ever want to have some fractions and some not fractions. That's just stupid. I will always make everything if there's one fraction, I want everything to be fractions, or I want no fractions, but never halves and halves. How many fractions do I have on this side, Carly? How many do I have on this side? What would be a good strategy? Try and combine this as 1. I'm trying to teach you how my brain kind of uses breadcrumb hints to decide my next strategy. I can often look at the question and figure out what the heck I need to do, even if I have no idea where I'm going, and I don't right now. I would want to write this as 1 fraction. Now, if I was multiplying fractions, that's easy. It's top times top, bottom times bottom. And Emily, if I was dividing, it's almost as easy. It's multiplied by the reciprocal. But adding and subtracting. You know what I need to add and subtract? I need a what? Common denominator. What's my denominator here? What's my denominator here? What is 1 over 1 as something over x squared? Ellen. Now I can write this as a single fraction over x squared. Now, Brianna, I love identities for 2 reasons. First of all, they're brain teasers. But secondly, and I'm going to try to pass this off to you, suddenly, one or two lines from the end, most of you will suddenly see it, and you'll get a little nerdy adrenaline rush, a little aha moment. That's our goal, to try and spot and try and solve these. The top would be x squared plus y squared. Yes? Anybody see it yet? Ellen, what? So, what? Now, the other reason I was pretty sure that was the case is, does the denominator match the denominator? Then I'm pretty sure the top has to match the top, and I do get my little nerdy adrenaline. Aha. And I say Q, E, D. Look at your formula sheet. Is 1 plus tan squared equals secant squared on your formula sheet on the top row there? Say yes. It is there, yes? Top row, yes, Tyler? You found it? Those are, by the way, those three are called the Pythagorean ones because they all have squareds in them, like a squared plus b squared equals c squared. So the first one, sine squared plus cos squared equals 1, that's one that you'll memorize. You'll use it so often you will. By the way, all three of these actually have, all of those Pythagorean identities actually have, I'll get it for you later, actually have three different equations, because not only is 1 plus tan squared secant squared, isn't this true? Yes? Oh, and isn't this true? Okay. So get good at rewriting things in your, each one of those, Maria, has three little different equations, because you could get any one of those three things in the top row by itself. Okay. The same way the base identities can be used to prove that. And from now on, we are no longer going to go back to x and y and r. From now on, we are going to use these five. The fact that tangent is sine over cosine. The fact that cotangent is cos over sine. The fact that sine squared plus cos squared equals 1. 1 plus tan squared equals secant squared. 1 plus cotangent squared equals cos secant squared. These are on the formula sheet. And remember that they can all be rewritten. So we only use x, y, and r to prove these ones. We already have. We're now going to get busy. So it says, before considering more complex identities in the next lesson, we're going to review some skills in simplification and factoring. So turn to page 338. On your test, on the multiple choice section, I'm probably going to say to you, simplify. And what it really means is rewrite this as a single trig ratio. Then it says use a graphing calculator to verify. Forget it, we're not going to. So this is not a t-table proof, because they didn't give me prove one thing equals something else. They just left this wide open. They said, you know what, Ryan, if you do your work, you can write this as a single trig thing. Not with a sine squared and a cos squared and a plus 1. Apparently you can write it as one thing. Okay. Let's see if we can do that. What if this was sine over cos from your formula sheet? What's sine over cos the same as? Tangent. So what's sine squared over cos squared the same as? This is the same as tan squared x plus 1. Hey, 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 I've seen this before. Check the top row somewhere on your sheet. Yes, 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 yes. What's tan squared plus 1 the same as? Done. I rewrote that as a single trig function. What did I write it as? Secant squared. B. Okay, strategies. One of the first strategies that I go to is I try and rewrite everything in terms of sine and cosine. So every tangent becomes a sine over cosine. What does every cotangent become? Cos over sine. So sine x plus, this is going to be cos x over sine x times cos x. Now I want you to notice how I wrote this. If you put that cos x, down here, you're silly. Because what's that cos x over? It is a fraction, and if I have one fraction, I want everything to be fractions, and now I can see what's going on better. By the way, this will be the unit where you will go from sucking at fractions to becoming at least mediocre at fractions, and some of you may even become tolerable at fractions. I have hopes that maybe even one of you might become okay at fractions. These two are being multiplied, and BEDMAS says I have to do timesing before I add. How do I multiply two fractions together? Top times top, bottom times bottom. Thankfully, that's the easiest one. So this is going to end up being the sine x over 1 just carries. And you'll get cos times cos, which is just cos squared, over sine x. Is that okay, Tyler? Now I'm adding fractions. To add two fractions, what do I need? Common denominator. What's the denominator over here? What's the denominator over here? What is my common denominator going to be? Okay, it's going to be sine. I'm going to write this as a single fraction over sine x. Now, if we're lucky, some of you might get your nerdy adrenaline rush in the next line. We'll see. First of all, what would I multiply? This is how you find a common denominator when it's algebraic. Eric, what would I multiply a 1 by to turn it into a sine x? It's meant to be really obvious, but also tricky. I'm going to multiply the bottom by sine x and the top by sine x. Now, some of you will be tempted, look up, to just write that. I will take a half mark off for that because that is wrong. You have not multiplied the top and bottom by 1. You have not multiplied the top and bottom by the same thing. You've completely changed the question. And even if you do it right on this line, I guarantee, Spencer, you're setting yourself up to make a dumb mistake later on. Trust me. So I'm going to insist that you show what you multiplied the bottom by and the top by. By the way, what is sine times sine, Eric? Yes. And then what was next to this fraction? What symbol? Eric? What was next to this fraction? What symbol? Plus. Drops down like a domino. And then over here, this one's already over sine x. It's already over the common denominator. Yes? So I can just drop it here. Hey, hey! I've seen that sine squared plus cos squared. That's on the top row. In fact, that's the one I told you to memorize. What is sine squared plus cos squared the same as? That's the nicest identity of all, because that one shows up a lot. And Maria, can we suggest that replacing something with a 1 makes things easier usually? Yes? So you're telling me this is the same as 1 over sine x? Oh, and hey, what is 1 over sine x as a single trig function? This whole thing is actually cosecant in disguise. Example 5. Express that in terms of sine A and cos A and write in simplest form. So now it's saying you may have a sine and a cosine left behind. Okay. First thing I'm going to do is replace everything with sine and cos. What's tangent in terms of sine and cos? Okay. Put your pencils down for 1 second. I'm going to show you the, and I'll say it, the stupid way to write this. And I see this all the time, and I need to, Asar, lovingly beat this out of you. Kids will go, oh, it's a fraction. And they'll go, it's a sine over cos, and then they'll do that. Why is that so dumb? Hey, that 2, is it on the top or the bottom? Can you tell right now just by glancing at it? Dumb. That's a fraction 2. What is it? It's on the top. It's over 1. And I took 1. I said it's 2 over 1 times sine over cos, which is going to be 2 on the top and a 1 on the bottom. And I didn't bother writing the 1. Okay? Stop writing some things as fractions and some things as single level numbers. If you have one fraction and you see it coming ahead of time, start thinking everything that's on the top, everything that's on the bottom, write everything as fractions. 1 plus tan squared. Now, I could write this as sine squared plus cos squared, but this is twigging me. Isn't this on my sheet somewhere? Oh, what is it? I'm not done, but I would argue, Mitsu, that looks nicer. This is written in terms of sine and cos. This is written in terms of sine and cos. This is not. Secant is what over what? 1 over cos. So what would secant squared be? 1 over cos squared. So the top is still going to be 2 sine A over cos A. The bottom is going to be 1 over cos squared A. Oh, ha. Do I have one fraction over another fraction? How do I divide by a fraction? So this is going to be the same as 2 sine A over cos A times cos squared A over 1. By the way, those of you that have me in physics know how much I loathe writing over 1s and extra 1s. The fact that I'm insisting that you do it would suggest that I think it's hugely helpful and hugely crucial, because I'm writing extra stuff which normally I loathe doing. Oh, hey! How do I multiply fractions? Top times, bottom times. But I can be clever. How many coses are there on top? Can you see it? 2. How many coses are there on the bottom? That'll cancel one of those out. And I'm left with a 2, a sine A, and a cos A. And if this is multiple choice, that will be one of your answers to pick from. Now that's just playing around with trig expressions, doing some factoring, doing some fractions, doing some basic math. Let's actually go to solving some trig identities. So we're going to jump to the next lesson. Really? Yeah, lesson 6. Page 344. Now on page 344, the author has their hints for improving an identity. I actually gave you a sheet, and sorry, you can't have this sheet on the test, but on the sheet, I have hints for proving trig identities. I think mine are better. I have a few other things worked in there. So keep that sheet where it says hints handy. Keep the formula sheet handy. And we're going to jump straight to example 1. Now, example 1 says, consider this statement here. It says, verify that it's true for pi by 3. It is. If you put a pi by 3 right there and a pi by 3 right there and go to your calculator, and you put a pi by 3 right there and a pi by 3 right there and go to your calculator, it is. B says, use a graphing calculator to show that this is an identity. What they mean is, if you graph that as left side, y1, and you graph that as y side, y2, you'll only get one graph appearing on your screen because they're the same graph. That's a way to check, but we're not going to solve them that way, Maria. What we're going to do is see. First thing I'm going to do is copy out the question. 1 over cos theta minus cos theta. And I want to show that that equals sine theta tan theta. Okay. Kara, what's hint number 1 on my sheet? Begin with the more complex or uglier side. Both of these are ugly. I'm going to be doing work on both sides. What's hint number 2, Eric? Not from my sheet, please. Mine is better. I have cosine, that's 1 trig function. I have sine, that's 2 trig functions. I have tangent, that's 3 trig functions. Do I have more than 2 trig functions, Eric? Then let's rewrite everything in terms of sine and cos. That gives us a goal. Okay. So I'm now going to work on the right-hand side. I'll rewrite the sine theta. What's tangent in terms of sine and cosine? This is dumb. This is clever. Why create possibilities for you to get things mixed up? Because now I know what to do on the right-hand side. Do I have 1 fraction times 1 fraction, Mitsu, on the right-hand side? Then how do I multiply fractions? That's the easiest one. Top times top, bottom times. So what is sine times sine, Asar? And what is 1 times cos? And I think I'm done with the right side for now. I can't see anything else. But here's what I notice. How many fractions do I have on the right-hand side? 1. How many fractions? Oh, by the way, folks, I should have done that as soon as I had fractions. Yes. How many fractions do I have on the left-hand side? So give me a suggested strategy. Take the left-hand side and write it as what? 1 fraction. How? Common denominator. Now, I have no idea where I'm going, but I'm going to keep my eyes open, and I'm going to always move my eyes from left to right, because I'll show you some little breadcrumbs along the way where you can suddenly go, I'm on the right track. What's my common denominator here, Spencer? So we're going to write this all over cosine. Oh, the first fraction is already over cosine, so the 1 would just drop down, and the minus sign would drop down. Yes? By the way, here's my first breadcrumb. Emily, what's on the bottom of the right-hand side fraction? What's on the bottom of my left-hand side fraction, even though I'm not done? I think I'm on the right track. Yes? Emily, what would I multiply a 1 by to change it into a cosine? On the bottom and on the top. Emily, what is cos? What's another way of writing that? Good. Hey, I've seen a cosine squared somewhere on my formula sheet, the top row there somewhere. What is 1 minus, you have to do some math in your head, a little bit of algebra in your head. What is 1 minus cos squared the same as, apparently, from that top row? Is it the same as sine squared if I rearrange that one? And is that what I wanted on the right-hand side too anyways? And I have to because I'm a nerd, right? Q, E, D. There's my touchdown. Spike the ball. Question easily. Quo ertas demonstrandum. Question easily done. That's an identity. 1, 2, 3, 4, 5, 6 lines. 12 lines. We'll get there. D says, oh, by the way, state the restrictions. Okay. Oh, you know what? Cosine theta can't be 0 because in this fraction I'd be dividing by 0. Here, no problem. Here, no problem. Now, tangent, although at first it didn't look like a fraction, it is a fraction. What's on the bottom of tangent? Cosine. Cosine can't be, oh, I already wrote cosine can't be 0, but even if I hadn't had the cosine on the bottom over here, that restriction still would have popped up here. Next page. Consider sine theta over tan theta equals cos theta. Let's prove it. So we want to prove that sine theta over tan theta equals cos theta. Ryan, what's the first hint that I gave you on the sheet that I gave you? Read it to me. Which side looks uglier, left side or right side? This one's fairly obvious. Left side. I'm going to be doing most of my work on the left. It's far easier to take something ugly and make it look pretty than to go the other way around. Tyler, what's hint number 2? Stop. 1, 2, 3. I got more than 2. Yeah. Okay. This is already signed, so I'm good with it. Over. Oh, what's tangent? And the right-hand side already is cos theta, so I'm good with that. By the way, this is really, technically, that's really sine over tangent, is it not? Now, why did I do that? Because now, Asar, I clearly have 1 fraction divided by 1 fraction. 3 levels. Many of you aren't sure. Hey, what's on the top? What's on the bottom? Wait, where in the middle? Is that on the bottom on the top? Or is that on the top on the bottom? You never need to make that decision. Put stuff over 1. How do I divide by a fraction, Isabel? Caught you mid-yawn. So you're saying I'm going to go times sine theta over 1 times cos theta over sine. Ah! Ha ha ha! Got my nerdy adrenaline rush. Because how many sines are there on top, Isabel? 1. How many on the bottom? What happens to those sines, Isabel? And I'm left with cos theta over 1, or just plain old what? Cos theta. Q. E. D. D says, state the restrictions. Well, when I wrote everything in terms of sine and cos, the only thing that I had in the bottom of a fraction that wasn't a 1 was cos theta couldn't be 0. All right, example 3. This is a little more like it. Example 3, this would, by the way, C minus level, C level. Really? What's the A level? Oh, wait, we'll get to those. Prove this. Which side do you think I'll be spending the most time on, the left side or the right side? I think the left. Is there more than 2 trig functions? 1, 2, 3. Yeah, you know what? I'm going to rewrite everything in terms of sine and cos. And even though this is my own preference, the left side I'm going to be spending more time on. I'm going to start with the clean side, finish it, and quit. First of all, cosecant is what over what? 1 over sine? What's 1 over cosecant then? This is just plain old. The reciprocal of the reciprocal is no more reciprocal. That's why I did that one first, because I knew I could stop there. Can I do anything else with that side? No. Apparently, this whole left-hand side will work out to sine theta. Maria, what was the first hint that I gave you? Second hint that I gave you? Everything is in terms of sine and cos. Maria, what was the third hint that I gave you? That's what we've been doing, for example, when we pulled out that sine squared plus cos squared. We've done a few of those. I don't have anything on my sheet with a sine cubed in it, do I? Say no. And although I have a cos squared, there's a sine attached. No, that's not good. Hint 4, Maria. Stop. Look to factor, especially GCF. Is there a greatest common factor here? What? Oh, let's factor out a sine. And I'll have a cos squared. Oh, sorry, I just got my nerdy adrenaline rush. And a sine squared. We're one line from being done. Let me see it. Sabina, what? What is cos squared plus sine squared apparently the same as? You're telling me that this whole thing is just a 1? So that this whole thing just equals... Question really... Oh, I know, that's not really. Question easily done. Quo ertas demonstrandum. Sheesh, that was 3 lines, Mr. Dueck. Bring them on, I say. Bring them on, I say. Let's do that. Turn the page. Prove that sine A plus tan A all over 1 plus cos A equals 1 over cotangent. I'm going to cheat. Yoink, there. Because I know I'm not going to have room to rewrite it and have enough room to do work. So I'll just do that. Oh, it asks for what values is this undefined. We'll do that at the end. Okay, which side do you think I'm going to be spending the most time on? The left. Are there more than 2 trig functions? Yep. I'm going to rewrite this in terms of sine and cos. But let's do the right side first. If it just said cotangent, cotangent is what over what in terms of sine and cos? Cos over sine? What would 1 over cotangent be then? Wouldn't be cos over sine. You know what it would be? Sine over cos. Also because 1 over cotangent is just tangent, which is sine over cos. The right side there, sine A over cos A. And I think I'm done with the right side. The left side. Let's rewrite everything in terms of sine and cos. Sine A plus, what's tangent? Sine A over cos A. Ellen, did I just write a fraction? I'm going to go back and put that sine A over 1. All over 1 over 1 plus cos A over 1. And I'm about to show you a trick that is glorious, a math shortcut that is wonderful. First of all, I need to describe this. Alex, we call this a complex fraction because it has many fractions inside of a big fraction. It's fractions inside of a fractions. Technically, this was a complex fraction as well, but that was 1 fraction over 1 fraction, and that we can deal with by saying, how do I divide by a fraction? Flip it and multiply. That does not work here. And, oh, what's hint number 5? Okay, don't cancel unless you factored. I see kids sometimes, I want to cancel out cos A. Have I factored? Can I cancel? Hint number 6. Do I have a hint number 6? Ah, let's all look at hint number 6. And Maria, read it out in a big, loud voice. I do. Multiply the top and the bottom by a common denominator. What's on the bottom of this fraction? Brett. Here, here, here. What's the common denominator of those 4 mini fractions? So here's what I'm going to do. Bracket, 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 bracket. I'm going to multiply the top and the bottom by cos. Except, look how I'm going to write it to make dumb mistakes minimal. Some kids don't write this down, don't write this down. I see some kids, they go like this. Oh, I'm going to multiply the top by cos and the bottom by cos. To me, that's dumb because how many levels does this fraction have? How many levels does this fraction have? Why confuse yourself? Here's what I'm going to write. I'm going to multiply by cos over 1 over cos over 1. Is that still multiplying the top and the bottom by cos, Emily? Yep. Oh, and notice what this really is. What is cos over cos? What am I really multiplying by? A 1. So I'm not changing the question, because if I multiplied by something else, I'd be changing the question, and now the identity is no longer true. I'm multiplying by a 1, but it's the common denominator on the top and on the bottom of all my mini fractions. Why is that so nice? I'm going to multiply that. I'm going to get sine A, cos A. I'm going to multiply that. Oh! When I multiply this times this, how many coses on top? How many coses on the bottom? This is just going to end up being plus, and I'm running out of room. I apologize. So I'm going to have to cheat. Do that. Huh. Sorry if you can't. I'm just going to get a plain old sine A. And you'll notice now all the fractions on the top are gone. On the bottom, will anything cancel in the first term at all? No. It's going to be cos A plus. Will anything cancel in the second term? No, it's going to be cos times cos, which is what? Now this may look uglier to you, but first thing I want you to notice, how many levels does this have now? 2, much nicer. And I guarantee if you do this almost always, you'll be able to factor a GCF. GCF on the top is what? And I have cos A plus 1. GCF on the bottom is what? Yeah. I did multiply everything by cos A. Not sure what you're asking me. Say it louder again. That there. Why did I multiply by the cos? Okay, first of all, I have to multiply by a 1. Okay, I can't just suddenly go, I'm going to multiply the bottom by cos. You just totally changed the question. What I'm showing you is it's called canceling complex fractions. And what I'm saying to you is if you have a 4-level fraction and you want to rewrite it so it's the same thing but looks nicer, you multiply by a 1. Is that a 1? Say yes, Brett. It is. Isn't cos A over 1 divided by cos A over 1? Isn't that the same as a 1? Which one are you going to choose? The trick is, look at the common denominators of each of the mini fraction, and I guarantee then if you multiply the top and the bottom by that common denominator with the common denominator on the top, you'll cancel out your complex fraction. You'll be left with 2 levels. This green fraction is the same as this blue one, where if you had just multiplied a cos in here, you've completely changed the question, because now you haven't multiplied by a 1, you've multiplied one thing by a cos, which totally changes the question. It's illegal. Let me come back to answering your question in a second, because I want you to see what's going to happen here. Okay, Brett? Brett, what's the GCF on the bottom? Oh, I was doing black, Mr. Dueck. What's left behind when I factor a cos A out of a cos A? What's left behind when I factor a cos squared out of a cos? By the way, what was the GCF on the top, Eric? What's on the top over here? What was the GCF on the bottom? What's on the bottom over here? Oh, what can I do with those two things? You mean a cos A plus 1 and a cos A plus 1? How many cos A plus 1s do I have on the top? 1. How many do I have on the bottom? That's the complex fraction trick. It says if you have a complex fraction, put everything over 1 first of all, so you have 4 levels, clearly. Find your common denominator and multiply the top and the bottom by that common denominator. And the best, easiest way to do it, Brett, is to go over 1, and then FOIL, right? Distribute. And you'll always cancel out all the fractions on the top and all the fractions on the bottom. You'll be left with 2 levels, and I guarantee 99% of the time there'll be a GCF that you can factor out. And 99% of that time, the brackets will cancel. There are other ways to do that, but nothing that gets you there in 1, 2 lines. Example 5. By the way, we're going to go right to the tone. Your homework is going to be nothing right now. We'll pick this up after spring break. Example 5. Yoink. Well, how many different, start with the uglier side, this one, and how many different trig functions are there in this question? Secant and cosecant. 2. I don't think I'm going to rewrite everything in terms of sine and cos. You could, and you would still get there, but not in the shortest path possible. I'm going to work with the left-hand side. This denominator is twigging me. Secant squared minus 1. I've seen that, sort of. Have I not? It's tan squared? So you're telling me that this is really the same as secant squared over tan squared? Okay. Oh. 1 trig function, 2 trig functions, 3 trig functions. I think now I'm going to rewrite everything in terms of sine and cos. So this is going to be, secant goes with cosine. This is going to be cos squared over 1 all over sine squared over cos squared, because tangent is sine over cos. Yeah. Thank you. Whoops. Brett, this is also a complex fraction. It's got 4 levels, but is it 1 fraction over 1 fraction? Oh, then how do I divide by a fraction? Flip the second one and multiply. I just got my nerdy adrenaline rush. I see where we're going here. Brianna, how many cos squareds on top? How many cos squareds on the bottom? Yes? And I get 1 over sine squared. Hey, wait. Okay, I'll write that. And what is 1 over sine squared, Brianna? Cosecant squared? Q, E, D. I forgot to do something a couple of questions ago. Can you turn back to question 4 here? I forgot to say for what values is this identity undefined. Okay. Well, from here, cosine of A can't be 0, yes? When I rewrote tangent, I also got cos A on the bottom, so that can't be 0. There's one more. Why can't cosine of A equal -1? In my original fraction right here, if cosine A worked out to -1, and cosine is -1, I think at pi, I would get 1 plus -1, which is what? Can I divide by a 0? Nope. Those are your restrictions for that guy. I'm going to pause. I'm going to give you about 7 minutes to practice a few of these. Can you turn back one lesson, please, to lesson 5? Page 339. Actually, page 340. See if you can try number 4. Number 6. Seven, 8, 9, 10, 11. Yeah, 13 is fine. I'll quit there. Okay. We're going to spend lots of time on this. Identities.